7.2. Now, maybe after 7.1 you had a question, and this is the same question I ask when I do these confidence intervals in different situations. Is maybe it came up in 7.1 that you said, well, if I know the standard deviation of the population, why wouldn't I know the mean in that case? And you're exactly right. It's more harder to find the standard deviation of a population than it is just the general mean of the population. So, if you had a question in 7.1, why that was, that's a legitimate question. It was just kind of covering all its things there. So this is 7.2. I think is a little bit more applicable to a situation that you might find yourself in, and that is that you went out and did a study with less than 30 people, and you got the mean, you got the standard deviation of the sample, and you just want to figure out with confidence, create a confidence interval, what the general population's mean is going to be. Now, there is some things you have to remember, though, with the sample. In order for this to work, the sample that you have has to be normally distributed. And as we looked at in 6.2, towards the end of 6.2, there was a way for you to determine if data is normalized. And you can go check that out if you want. Please assume that the problems that you are doing, it's already said that the sample you have is normally distributed. So we don't have to worry about testing of that, and I'll explain that more as we get to a problem like that. What you'll notice, I'm going to explain two new concepts that in a new chart we're going to use. I'm going to explain degrees of freedom. Now, this is going to be used quite frequently in statistics moving forward here, and I'm going to try my best to explain degrees of freedoms. For you guys that were in calculus one time, at one point, you might have heard we talked about limits, and then it came to the conclusion that at the end of all the limit and talk that it was just like that's all it is. And so it's kind of like what degree of freedom is. So I'm going to briefly take about 2 minutes of your time and try to explain this degree of freedom, and then I'll explain how it's applied to what we're doing. So what degrees of freedom are, if I'm going to use a stats example here, it's the level of which numbers in the data are free to be different. Okay, so for example, let's just talk about an example of stats. This goes back to our unit 3 here, where let's say I have data here 5, 10, and 15. Let's just say how many. Let's say pencils I have in my locker. So I have 5 pencils, maybe somebody else has 10, and Mr. Miller has 15. So we add up all our pencils together, we would get 30, divide by 3 of us. So we would say that our mean is 10. All right, so a standard little problem there. Add them all up, divided by 3. And then if I wanted to find the deviation of each of our data points, I would subtract the mean from each individual point, and I would come up with the standard, or not the standard deviation, but just the deviation of the mean. So like for me, having 5 pencils in my locker, I'm -5 away from the mean. We'll say Mrs. Gabi has 10. She is right on the mean. And then Mr. Miller has 15. So he is, well, you can probably guess what that's going to be, right? Which is 5, right? Because deviations all have to equal 0 at the end, right? So some of you guys already made that conclusion. You said -5 plus 0, well, plus 5 would equal 0, and I've kind of written this out horizontally here. So we know that that question mark would have to equal 5, all right? Yeah, that's pretty self-explanatory. If you've been in any algebra class, that would make perfect sense, right? So why this applies to degrees of freedom is that you'll notice that at this last number, this has to equal 5 because we know the deviation has to equal 0. So this last number has no way of being any number at once. These two previous numbers have a level of freedom that they can just be any numbers they want. I just know that my last number that I have to plug into this has to make it true. So on a more abstract reason, I could say, well, this first number could be 7. Let's say it has to equal 0. This number could be, let's say -5. And then we say, well, what does this third number have to be? Well, we're restricted. It has to equal, in this case, -2. So the degrees of freedom, we could choose any 2 numbers. These can be any numbers we want to roam free, to be whatever numbers we want. We just know that the last number has to make it so it equals what we want. So this last number doesn't have any freedom at all. Another way to look at it a little bit more abstractly is if I got in my car, left the garage, and I just drove anywhere I wanted to in Muscatine. So I just drove to Walmart, and then I decided to drive to Hy-Vee, but if I wanted to go home, let's say I can drive 3 places. The last thing I'm going to do, no matter where I went the 2 places, my route home is going to be restricted. I can't take a different route home, right? My route home is my route home. So I know in a nutshell, degrees of freedom is kind of a little abstract to think about, but in retrospect, and what it really means is, if we get down to it, is when I say degrees of freedom, we just take the number of the population or the number of the sample n minus one, and that would be the degrees of freedom. So if maybe the idea behind degrees of freedom is a little bit kind of weird, just know that when I say degrees of freedom, it's just the sample minus one. So maybe that helps to sum things up a little bit better for you. But I try my best to kind of explain what degrees of freedom, so it's not just some number I just say, hey, degrees of freedom, this is what it is. And so if you want more explanation, please email me and I'll hopefully explain a little bit more. Okay? So I'm going to show you where this comes into play, this degrees of freedom thing. You'll notice that this formula right here looks very similar to 7.1. And you'll notice maybe a slight difference, and that is that instead of our Z subscript here, it's a T, all right? And that's really, you'll also know that it's not the population standard deviation, because again, we don't know what the population standard deviation is, so we have to use the sample standard deviation, which is the symbol S, and then we're going to do a very similar thing we just did on the last section 7.1, okay? Now, because we are using a different margin of error, in this case a t-distribution is going to be used, we have to use a slightly different chart. So what I have here is I'm going to bring up what you guys would see on your EICC Connect, and if I scroll down a little bit, this is the student view, hence the pink bottom and stuff like that. So if I were to, I guess I have to leave the student view because I need to access 7.1, which I haven't put up yet. So let me giving you guys a preview of what to look at here. So 7.2 is what we're working on here, and so if I look at this page, which you guys will have access to this, I have something called the t-distribution chart. So you want to pull that up. All right, download it here. And you'll notice this is a chart from your book. It's Appendix C. Obviously, some of you guys don't have your book. If you do, you can find it. It's a table F, and this is called the t-distribution. So instead of using our normal distribution chart, we're going to be using this t-distribution. All right, and pretty much the same rules apply here. One thing, let me move this over here. One thing I want you to disregard is this one-tail, two-tail stuff. Don't pay any attention to that. That's something we're going to look at in the future. And for right now, so all you care about is the confidence intervals, which you should be familiar with from our last section. And then we have the degrees of freedom, which we just got done talking about. Okay? So let me show you how that applies to a problem here now. So a recent study of 28 employees at the XYZ company. So let me, this is problem number 11 in your practice problems, is I'm going to dissect this, and we're going to have, I know that the number of people that are in the study is 28, okay, in the sample, I guess, showed that the mean of the distance they traveled to work was 14.3 miles. So the sample mean is 14.3. The standard deviation of the sample mean was 2 miles. So my sample standard deviation is 2 miles. And I'm looking for the 95th percent confidence interval, 95% confidence interval. So I'm going to put that down, 95%. All right, so I need to transfer that into my t-distribution. Now this is where the degrees of freedom takes effect. So I'm just going to write that in there too, d period f, which is the shorthand of that you'd find in stats, or df, would be n minus 1. So that would be 27. Okay, so I'm going to look at my chart here. You'll notice that instead of a z-score on the side, you'll notice on the side here it has df. All right, that means degrees of freedom. So I'm looking for 27. I'm going to go across here the best I can. 27, and let's see. I need the 95th percentile, or sorry, 95th confidence interval. So that is 2.052. 2.052. All right. So 2.052. Now, similarly to what you just did on 7.1 is what you're going to do here. You're just using some different numbers. So we have the sample mean, which is 14.3, minus 2.052 parentheses 2 over the square root of 28. All right. Again, that 27 only takes effect when I look at the chart, so it's not going to be the n in here. The degrees of freedom only takes place when we look at the chart. There, and then we just copy the same thing, 14.3. In this case, I'm not going to forget, and I'm going to make that a plus 2.052 parentheses 2 square root 28. So, like I said, a very similar process to what you just did in 7.1. Now, when I put this data together, I get 13.5 parentheses u and then 15.1. So I just really want to quickly talk about the rounding rules for this so that I didn't make that clear in 7.1. And that is when we look at the how we round this, you'll notice that in this case I was given just the sample mean and standard deviation right from the start, and it is 14.3. So if you're given the sample mean in the problem, that's going to be what we round to for our confidence interval. So you'll notice I round to the nearest tenth. All right. You'll notice that on this next problem I'm going to do in the follow-up video is that I'm given the data. In this case, I would go, because I'm given the raw data, in my answer, I'm going to go one more decimal place over from my raw data. So in this next problem, I'll do the nearest tenth. Okay. So my answer is 13.5, so I'm guessing that the population mean, with 95% confidence that the population mean of my data is between 13.5 and 15.1. The follow-up question to this is, if a manager wanted to be sure that most of the employees would not be late, how much time would he suggest they allow for the commute if the average speed were 30 miles per hour? Well, you're guessing that the average person of the population drives between 13.5 and 15.1. So I would say that 15 would be a pretty good. That would cover most of your population, so 15 miles. So to drive 15 miles would take 30 minutes. So he's saying, based upon the sample I received, information I have, I would say that allow everybody about 30 minutes to get to work. That should cover pretty much the whole population with 95% confidence. All right, in the follow-up video, I'm going to do problem number 10 real quick when you're given the raw data. All right, thank you, and please come with your questions if you have them.